So now in unit number 3, that is the design against fluctuating load, the next topic is the stress concentration factor. We already learned about the stress concentration in the previous slide. Now we are going to see about the stress concentration factor. Now what is stress concentration? I just want to take a revision first. That stress concentration is nothing but it is defined as a localization of high stresses due to the irregularities present in the component and abrupt changes of the cross section. That means which we have seen in the previous one. Due to a point load or a load acting at only one point, or due to change in cross section, change in material, this can lead to a stress concentration. Now this is the stress concentration. Now what is the stress concentration factor? So in order to consider the effect of this stress concentration and to find out the localized stresses, a factor called as stress concentration factor is used, okay, to find out how much effect is being done by this stress on such a particular point. That factor is known as a stress concentration factor. Okay, that means we are considering on a single point only, and it is denoted by a letter k suffix t, that is kt, and in mathematical form we can show it in this way, that is highest value of the actual stresses near the discontinuity upon the nominal stress obtained by the elementary equation for minimum cross section. This is how we can do it. Now it can be written as kt is equal to sigma max upon sigma o, or you can say maximum shear stress upon the tau o, that is a nominal stress. Now where sigma 0 and tau 0 are the stress determined by the elementary equation. Okay, just remember this part. It is by the elementary, and sigma max and tau max are the localized stresses. Okay, so this is the difference. Now this subscript T denotes that it's a theoretical part. So stress concentration is a theoretical one. The magnitude of stress concentration depends upon the geometry of the component. But whatever the magnitude the stress concentration is having, that total depends upon the geometry of the component. It's circular, cylindrical, or spherical, like this. Now a stress concentration factor is the ratio of the highest stress, that is maximum sigma max, to the reference stress, that is sigma, of the cross section. As the radius of curvature approaches 0, the maximum stress approaches infinity. Note the stress concentration factor is a function of the geometry of a crack and not of its size. Okay, so stress concentration is a function of geometry of a crack. Okay, so it is a function of a geometry. Based on geometry, actually, this stress concentration work, not based on any sizes. That if the sizes is more stress concentration, less size, less stress concentration, not like that. Now stress concentration factor need to be used with ductile material when they are subjected to only static load. Okay, yielding will relieve the stress concentration, because in dynamic, if yielding occurs, then yielding relieves the stress concentration. That's the first static loading condition also it is considered. Now methods to find out the stress concentration. How we are going to find out where and at what place the stress concentration is more. So there are two basic methods, and one is the mathematical method based on the theory of elasticity, and one is the experimental method, that is a photoelasticity, which we can. For simple geometric shapes, the stress concentration factors are determined by the photoelasticity. For simple geometric shape, which we are going to see in the next slide, and the charts for stress concentration factors for different geometrical shapes and condition of loading were originally developed by R.E. Peterson. That means for mathematical method, a charts has been developed, which is developed by R.E. Peterson, and he developed some chart which I will show you in the next slide, which will help you to understand with the geometry how we can check the how we can measure the stress concentration factor. Right now we are not going to in the current stage in this global environment or in this design environment. Right now, all things are done with the help of some packages, that is the software packages. So FEA packages are used to find out the stress concentration right now. We are not going to use that graph or photoelastic method anymore right now. But to understand that part, we are going to see. Now this is photoelastic method. The stress concentration can be seen by photoelastic method. It is a method where a plain polarized light is passed through a photoelastic material. One transparent plastic material is there, and a photoelastic, or you can say the polarized light, is passed through that material, and based on that a colorful fringes pattern has been developed on that, and that pattern gives us where the stress concentration is more and where it is less. Let's see it. As you can say, the photoelastic coating are used to analyze the surface stress in bodies of complex geometries also. So this is how the photoelastic images look like. Okay, now this is not an exact, because the material is different, condition is different, but we can get something that here the concentration is more, here the concentration is more, here it is localized stresses. Now see here, yielding occurs, as I told you, yielding relieves the stress concentration, this curve shows. Okay, now here also it is been generalized. So this is how it has been developed. Now R.E. Peterson developed some charts. This is a chart, okay, for a plate with a hole. Okay, a rectangular plate with a transverse hole. The formula is this: P upon W minus D into T, and based on this, this is the stress concentration, and this is D by W value. So if you get the D by W value, you can get the stress concentration for it. Next is for the stress concentration factor for flat plate with shoulder fillet in tension or in compression. See here, capital D by small d ratio is there, and this is R by D. So based on these two values, you can get the shear stress factor here. This is the formula for it. Then the chart for stress concentration factor for round shaft. Okay, fillet subject to tensile forces, bending moment and torsional moment. Everything I am going to show here in figure 1, 2, 3. That is tensile forces in figure 1, then bending moment in figure 2, and torsional moment in figure 3. The nominal stresses in these three cases. The first is the tensile stress. Okay, with tension. This is the formula for it. Sigma is equal to load per unit area, tensile forces. Now for the bending forces, mb y upon I, sigma 0 is equal to mb y upon I is equal to pi d raised to 4 by 64, and y is equal to d by 2. Here you will get a bending value. Then torsion value, that is tau is equal to mtr upon j, where j is equal to pi d raised to 4 by 32 and r is d by 2. So these three values you can get for a shaft with shoulder fillet. Now the conclusion on this chart is that the model using a circular polariscopic or theoretical or finite element analysis of the mathematical model. So this is called a theoretical stress concentration factor, and either the photoelastic analysis or anything you can see the epoxy models. Here in photoelastic method, actually the model is made from different materials. That's why the actual material of a component is different. So ductility and materials, all these things are different. So we can't say that it's give a proper result. Therefore, there is a difference between the stress concentration indicating the theoretical stress and the actual stress. This is the reason because which we are getting it is totally different. Now, it is possible to find out the stress concentration for some simple geometrical shapes using the theory of elasticity also. Okay, this is, we can see stress concentration due to elliptical holes. So this is the formula for this, where A is the half weight, B is the half weight. Okay, and as B approaches 0, the ellipse become sharper and sharper. A very sharp crack is indicated, and the stress at the edge of crack becomes very large. It is observed from equation that if k is equal to infinity, when b is equal to 0. Okay, when small crack is there at that point, you will find more stress. So therefore, as the width of the elliptical hole in the direction of the load approaches 0, the stress concentration factor becomes infinity. Now the ellipse becomes a circle when A is equal to B. So at that point, Kt is equal to 3. Therefore, theoretical stress concentration factor due to a small circular hole in a flat plate which is subjected to tensile force is 3 for circular. Okay. So I think you have understand this part of stress concentration. So thank you very much for this.